We live in a world where everything around us has three spatial dimensions: length, width, and height, plus the passage of time, which we perceive as the fourth dimension. This familiar reality forms the foundation of our daily experiences. But what if there are more dimensions beyond what we can see or feel? Could extra dimensions be hiding in the very fabric of the universe, influencing everything from gravity to the fundamental laws of physics? For centuries, scientists and philosophers have debated the true nature of dimensions. In classical physics, the world seemed simple: three spatial dimensions plus time. However, as physics advanced into the realms of relativity, quantum mechanics, and string theory, the idea of hidden dimensions emerged not just as a curiosity but as a necessity to make sense of the universe. Some theories suggest there could be 10, 11, or even more dimensions, each playing a role in shaping reality in ways we can barely comprehend. But if these dimensions exist, why can't we see them? How do they affect the universe, and could we ever prove their existence? Exploring extra dimensions isn't just about abstract mathematics. It's about uncovering the deepest secrets of space, time, and reality itself. Our everyday reality is built on three fundamental spatial dimensions: length, width, and height. These dimensions define everything we see and interact with, from the smallest objects to the vast structures of the cosmos. Whether we look at a table, a mountain, or a galaxy, we describe them using these three measurements. To visualize this, imagine a simple cube. It has height, up and down, width, side to side, and depth, front to back. No matter how we rotate it, these three dimensions always exist. Every physical object we perceive fits within this framework, making three-dimensional space feel like the natural order of reality. The way we move in this space is also governed by these dimensions. A person can walk forward and backward, one dimension, move side to side, a second dimension, and jump up or down, a third dimension. Everything we interact with, cars, buildings, planets, exists within these three spatial dimensions. For most of human history, scientists and philosophers believed these were the only dimensions that existed. But as our understanding of the universe deepened, especially through Einstein's theory of relativity, we learned that there was another crucial dimension: time, which changes everything. While we move freely through the three spatial dimensions, time introduces a different kind of movement, one that is unidirectional and unavoidable. No matter what we do, we are always traveling forward in time. This is why scientists consider time the fourth dimension, even though it behaves differently from the three spatial dimensions we are familiar with. Albert Einstein's theory of relativity revolutionized our understanding of time by showing that it is not an absolute fixed backdrop. Instead, time is woven together with space to form what physicists call space-time. This means that time can stretch, compress, and even slow down depending on gravity and velocity. For example, astronauts on the International Space Station experience time slightly slower than people on Earth due to the weaker gravitational pull in orbit. This phenomenon, known as time dilation, proves that time is flexible and not the rigid universal clock we once thought it was. Another key realization from relativity is that space and time are deeply connected. Movement through space affects how we experience time. The faster an object moves, the slower time flows for it relative to someone moving at a slower speed. This effect becomes extreme near the speed of light, where time can nearly stop for a fast-moving object compared to a stationary observer. But while time behaves differently from spatial dimensions, it is still a fundamental part of our reality. It governs everything from the aging of living beings to the evolution of the universe itself. Without time, there would be no cause and effect, no past or future, just an unmoving, frozen existence. Yet, if time is just another dimension, could we manipulate it the way we do with space? Could we travel backward in time or explore alternate timelines? While science fiction loves to imagine time as something we can control, physics suggests that time may be an irreversible dimension, at least for now. However, when we move beyond four dimensions into the realm of string theory and extra-dimensional physics, the boundaries of what is possible start to blur. Could extra dimensions be detected? If extra dimensions exist, why haven't we seen them? The challenge lies in their size and accessibility. If these dimensions are as small as string theory suggests, curled up at the Planck scale, they are far beyond the reach of current microscopes or particle accelerators. However, scientists are actively searching for indirect evidence of their existence. One of the most promising methods involves the Large Hadron Collider, the world's most powerful particle accelerator. When particles collide at nearly the speed of light, they release enormous energy, potentially revealing new physics beyond the standard model. Some theories predict that if extra dimensions exist, the LHC might produce tiny black holes or cause missing energy signatures as particles slip into higher dimensions. While no such evidence has been found yet, upcoming experiments could push the boundaries further. Another potential clue comes from gravitational waves, ripples in space-time caused by massive cosmic events like black hole mergers. If extra dimensions influence gravity, their effects might appear in the way these waves propagate through the universe. Future gravitational wave detectors, like LISA, might provide deeper insights into whether gravity is interacting with hidden dimensions. Dark matter is another mystery that could be linked to extra dimensions. This invisible substance makes up most of the universe's mass, yet it doesn't interact with light. Some theories suggest that dark matter could be ordinary matter moving through a higher dimensional space, meaning its gravitational effects bleed into our three-dimensional world without us being able to directly observe it. While no experiment has confirmed extra dimensions yet, the search continues. If scientists find evidence, it would revolutionize physics, providing a long-sought bridge between quantum mechanics and general relativity, potentially unlocking secrets of black holes, time travel, and even parallel universes. If we discover that our universe is just one slice of a much larger multi-dimensional reality, it would reshape our entire perception of existence. If extra dimensions truly exist, their impact on our understanding of the universe would be profound. They could provide the missing link between quantum mechanics and general relativity, two of the most successful but seemingly incompatible theories in modern physics. String theory, with its extra-dimensional framework, suggests that these two might not actually be separate, but part of a much larger unified reality. One of the most exciting possibilities is that extra dimensions could allow for parallel universes. Some theories propose that our three-dimensional universe is just one of many floating within a higher dimensional bulk, like pages of a book, each existing separately but still part of the same structure. If true, this would mean that our perception of reality is severely limited, and that other universes, possibly with different laws of physics, could exist just beyond our reach. Extra dimensions could also revolutionize our understanding of gravity. One of the biggest puzzles in physics is why gravity is so much weaker than the other fundamental forces. Some theories suggest that gravity is actually just as strong as other forces, but spreads out across extra dimensions, making it appear weaker in our three-dimensional space. This could explain why we experience gravity as such a feeble force compared to electromagnetism or nuclear interactions. The discovery of extra dimensions would also have profound implications for cosmology and the fate of the universe. If higher dimensions influence how matter and energy interact, they could determine whether the universe will continue expanding forever, eventually collapse, or cycle through endless big bangs and big crunches. Some versions of string theory even propose that our universe was created when two higher dimensional brains collided, meaning the Big Bang might not have been the true beginning of everything. Beyond physics, the confirmation of extra dimensions would challenge our very perception of reality. If space itself is far more complex than we ever imagined, it raises deep philosophical and existential questions. What if human consciousness is tied to these hidden dimensions? Could advanced civilizations access or manipulate them? And most importantly, are we just scratching the surface of an even deeper, more intricate universe? For now, extra dimensions remain one of the most fascinating yet unproven ideas in modern science. But with future advancements in technology, high-energy experiments and deep space observations, we may one day uncover direct evidence that reality is far stranger than we ever imagined. If and when that day comes, it will be one of the greatest scientific discoveries in history. The search for extra dimensions is more than just an abstract scientific curiosity. It could redefine our understanding of space, time, and existence itself. From string theory's proposal of 10 or 11 dimensions to the possibility of parallel universes, hidden forces, and even new laws of physics, the implications are staggering. While no experiment has yet confirmed the existence of extra dimensions, cutting-edge research continues. The Large Hadron Collider, gravitational wave detectors, and future space missions may eventually provide the evidence needed to prove that reality extends far beyond what we can currently perceive. If extra dimensions do exist, they could unlock the long-sought theory of everything, bridging the gap between quantum mechanics and general relativity, solving the mystery of dark matter, and even explaining the origins of the universe itself. Ultimately, whether or not extra dimensions exist, the very fact that science is pushing these boundaries highlights the vastness of human curiosity. The universe, whatever its true nature, remains full of mysteries waiting to be uncovered. And as we continue to explore, we may one day discover that our reality is just a small part of something far more profound than we ever imagined.